Today's topic is multi-stage amplifiers. It's a very simple concept. We will be doing it in a superficial manner. We will not go into the exact circuit. We will not go into the detailed circuit here. Okay. Basically, multi-stage amplifiers is exactly what it sounds like. Multi-stage, more than one stage of amplifiers. So you'll connect the output of one stage to the input of the next stage. Why are we doing this? In order to improve some parameters like voltage gain, current gain, input impedance, output impedance, and so on. So you can control it better, all these parameters, as well as get improved values as per your requirement by doing this. A typical block diagram is shown here. This is the input voltage that is applied at the input of the first stage. Let us call the first stage having a voltage gain of A1. The output of that stage is connected to the input of the next stage. That is V1 goes to input of A2. V2 is the output of second stage that goes to the input of next stage, and so on. So you have n number of stages. Now you can actually have different configurations. In case of BJTs, you can have configurations like common emitter, common collector, and all that. You can have different combinations in order to achieve whatever you need for a particular application. Okay. Now what we will be seeing in detail is the effect on gain and the effect on bandwidth. What is the effect of cascading or the effect of having multiple stages on gain? Let us look at a typical block diagram once again. The first stage has a gain of A1 with a phase angle shift of theta 1. Second one is A2 theta 2. A3 is the gain for the next one, and theta 3, AN and theta n for the nth stage. Let's call it to have n number of stages. The input of the first stage is Vi. The output of the first stage as well as the input of the next stage is V1. Output of second stage V2, output of third stage V3, and so on. Output of n stages Vn. For the first stage, if I write the gain, it would be V1 output voltage divided by Vi input voltage, right? As simple as that. And that is denoted as A1 with a theta shift of phase shift of theta 1. For the second stage, it would be output voltage V2 by input voltage, in this case is V1. So V2 by V1. For the last stage, it would be Vn divided by Vn minus 1. Vn minus 1. Okay. With giving us a gain of An with an angle shift of theta n. Okay. If I want to write the overall voltage gain, after cascading so many amplifiers, what is the overall voltage gain? AV, denoted by final output, that is Vn, by initial input, that is Vi. Okay. Final output Vn by initial input Vi. Vn by Vi. That is equal to, you can write it as Vn by Vn minus 1 into Vn minus 1 by Vn minus 2, and so on till V2 by V1 into V1 by Vi. Okay. You can write it like this also. And we all know that the gain of Vn by Vn minus 1 is denoted as An, and V2 by V1 is A2. V1 by Vi is A1 with shifts of angles of theta n, theta 2, etc. When you multiply all these gains, the magnitudes can be multiplied directly. The phases will add up, obviously, isn't it? So A1, A2, so on up to An, the gains magnitudes are multiplied and the phase shifts are added. This is the effect of multi-stage amplifiers, or cascading, mind you, on voltage gain. Our next point here in question is, what is the effect on bandwidth? In order to understand the effect on bandwidth, I need to remember that bandwidth is actually given by is equal to upper cutoff frequency minus lower cutoff frequency, FH minus FL. Let FH and FL be the upper cutoff and lower cutoff frequencies of individual stages. Now let's take FL first. Okay, what is the effect of cascading on FL? When you take low frequency gain, AL of F, in terms of mid frequency gain, the equation is given by AL of F is equal to AM by 1 minus J into FL by F. We are going to come to a conclusion on what happens to FL. Okay, what happens to FL after cascading? Let us assume that FL becomes FL naught. after cascading. Okay. So FL becomes FL naught. That means the overall lower cutoff frequency becomes FL naught. What happens to FL to make it FL naught? What is the relation between them? Does it reduce? Does it increase? And by how much? Okay. The same thing we shall do for FH, and then we shall find the difference. Okay. And thus we will find out what is the effect on bandwidth. So let us start using the gain equation, and we will come to the expression for FL naught. What is FL naught? That is the lower cutoff frequency after cascading. Overall lower cutoff frequency after cascading. Let us start with the gain equation. As I said, AL of F is equal to AM by 1 minus J FL by F. Very simple equation. We have already studied this. If you have n such stages and they are cascaded, you have a multi-stage amplifier, and the overall gain becomes ALN of F becomes, you have n number of stages. So what happens to the gain? As we said earlier, gain is multiplied, A1 into A2 into A3 into so on. If the gain of all these stages is same, it becomes A raised to n. In this case, if I have 3 stages, it becomes A raised to 3. So if I have n number of stages, it becomes A raised to am, a raised to n, not am, a raised to n. And in our case, this is a. Al of n of f is equal to our expression whole thing raised to n. Okay. So am by 1 minus j into fl by f whole raised to n. Let us give this n to the numerator and the denominator. It becomes am whole raised to n by 1 minus j fl by f whole raised to n. If I take the magnitude of this expression, the magnitude becomes am the whole raised to n is actually the same because it's a constant value by, you have, this is a complex value. So what is the magnitude of a complex value? A minus jb is equal to, magnitude is equal to a square plus b square. That's exactly what I'm writing here. A square is 1 and b square is fl by f the whole square. That is equal to am the whole raised to n by root of, I am going to give it to the new exponent, that is n by 2. You have n here already and you have 1 by 2 of that is of the root. This is the equation you get for overall gain with lower cutoff frequency. Now we are going to assume that, as I said in the initial part, we are going to assume that the overall lower cutoff frequency is FL naught. Overall lower cutoff frequency is FL naught. Now we are going to write the same ALNF in terms of FL naught. What will it become? That is equal to AM whole raised to n, because I have n number of stages. Okay. And you have AM into AM so on, divided by 1 minus j into, it is no longer FL by F the whole raised to n, because we are not considering the n number of stages. We are considering FL naught as the overall lower cutoff frequency. So I can simplify it as 1 minus j into FL naught by F. And that's how you get the denominator like this. ALN of F becomes AM whole raised to n by root of, this is the magnitude, root of 1 plus FL naught by F the whole square. Simplify it and you get AM the whole raised to n by 1 plus FL, I can write it like this, AM whole raised to n by 1 plus FL naught by F whole square whole raised to 1 by 2. I can write it like this also. At FL equal to FL naught, what happens to the gain? It becomes total AM whole raised to n by root 2. Because when FL naught is equal to F, this becomes FL naught equal to F. At F is equal to FL naught, it becomes like this, isn't it? And FL naught by FL naught is equal to 1. 1 the whole square is equal to 1 itself. Okay. 1 plus 1 is 2. And 2 raised to 1 by 2 is root 2. That's how you get AM whole raised to n by root 2. We have got this much. Now what we are going to do next is, we will equate these two points. That is, I have the magnitude here, right? I have the magnitude here, and the same thing, I have the magnitude over here. Yeah, right. Now, if I consider that the frequency I am considering is F is equal to FL naught, I can equate these two. I can equate these two because both of them give me the overall gain at f is equal to fl naught. Let's do that. So this is this equation number 2, am whole raised to n by 1 plus fl by fl naught whole square. I have substituted f is equal to fl naught here in that equation. F is equal to fl naught. Since in the third equation, when you are equating it, equation number 3, it is already considered at f is equal to fl naught. I can directly write it as am whole raised to n by root 2. Okay, quite okay. Now you see that the numerator is common and you cancel it, and the denominators can be equated. Let's do that. Denominators equated, 1 plus fl by fl naught the whole square whole raised to n by 2 is equal to 2 raised to 1 by 2. If I square both the sides, it becomes this is squared, meaning it is multiplied by 2. This is also multiplied by 2. This cancels off and this cancels off. So you square both sides, you get whole raised to n is equal to 2. You take the nth root of both sides. That means divide by n. You take nth root on both sides. This is what I get. Okay. Rearrange it. F by fl naught, fl by fl naught whole square is equal to 2 raised to 1 by n minus 1. Take the root. That means instead of the square, this becomes square root. And you get fl naught is equal to fl by 2 raised to 1 by n minus 1. This is exactly what we are looking for. What happened to the lower cutoff frequency after cascading? That is FL naught. What was it before cascading single stage? It was FL. It became divided by 2 raised to 1 by n minus 1. When it is divided by 2 raised to 1 by n, the value increases because root of 2 raised to 1 by n. What is the maximum value that root of 2 raised to 1 by n can take? Root of 2 raised to n 1 by n minus 1 takes the maximum value when n is equal to 1. When n is equal to 1, it becomes 2 minus 1. That is root of 1. That is equal to 1. So FL naught is equal to FL. Any other value that you substitute here for n, you realize that it is not equal to 1. It becomes less than 1. Okay. FL divided by a value that is less than 1, obviously this whole value is increased. That is FL naught is larger than FL. What is the effect of cascading on lower cutoff frequency? It becomes increased. And by how much does it get increased? By the root of 2 raised to 1 by n minus 1. Okay. Let's go on to high frequency gain. Let's do the exactly same steps. AH of f is given by am by 1 plus j f by fh. This is the equation we already know. For n number of cascaded stages, it becomes whole raised to n. This whole thing raised to n. And we take the magnitude here. AH of f is equal to am whole raised to n by root of a square plus b square form, and you do that. Okay. Now, without thinking of the individual stages, we are going to consider that f is equal to fh naught is the upper cutoff frequency, and then the gain becomes ahn of f is equal to am whole raised to n by 1 plus j into f by fh naught. Then the magnitude can be written as am whole raised to n by root of 1 plus f by fh naught, the whole square in this case. At f is equal to fh naught, we already know that if you substitute f is equal to fh naught, this becomes fh naught, it will become 1 plus 1, and this becomes root 2 as we said earlier. Equating these two at f is equal to fh naught, equating these two equations 4 and 5, am whole raised to n by root of 1 plus fh naught by fh the whole square whole raised to n is equal to am whole raised to n by root 2. Okay. From here, simplify it exactly as we did in the previous case, and you come to the equation fh naught is equal to fh into root of 2 raised to 1 by n minus 1. So you see that fh naught is actually reduced by a quantity 2 raised to 1 by n minus 1 whole root. Bandwidth is given by, new bandwidth is given by fh naught minus fl naught, fh naught and fl naught we have derived. But you observe that the first term dominates this expression because this increase is not much. Therefore, overall, a reduction in bandwidth is actually experienced. So the new bandwidth is actually less as compared to the individual stage. Okay. This is the effect of multi-stage or cascading on voltage gain as well as bandwidth. So that's it for this topic. Thank you. Thank you.